Let's do some problems having to do with the SN2 reaction. The first thing is going to be to analyze the prospects for a proposed SN2 between bromide, and you can't just have a flask full of Br- without having some counterion. So sometimes in a problem you'll see a counterion like lithium plus included. Think of the counterion as really following along wherever the negative charge goes, but not being directly involved in the reaction. The proposal is to take bromide then, and to take as the electrophile an alcohol. So this would be ethyl alcohol. So this is an alcohol. And then what we're trying to do is we're trying to generate as our product something that has bromine incorporated into the organic molecule. And so we could say SN2 question mark. The first part of this problem, I'd like you to think about this possible SN2 reaction and just complete the equation. In other words, something else is going to be released in the course of this supposed reaction, and the lithium cation is going to go along with it. So push the arrows for an SN2 going left to right, and then fill in the box. In this proposed reaction, the bromide is going to act as the nucleophile. Let's fill in all the lone pairs on bromide. And the carbon that's undergoing substitution is this carbon right here. And so in terms of the arrow pushing, we would start from the nucleophile. We're going to make a new bond to carbon, and then we're going to break a bond. Let's include the lone pairs here as well, just for completeness. We're going to break a bond in that way. So as far as the products are concerned, you would expect to get this. What would you name this? So type into your typing area. What is the name of this compound? This has a CH3CH2X type of structure. So that is an ethyl group. And then the thing that's attached here is a bromine. So this would be ethyl bromide. And then as far as what's in the box here, did you draw it in? Try again if you haven't. The thing that would be released would be this, hydroxide. So I'd like you to evaluate this left to right reaction, particularly in terms of the leaving group. Knowing what makes a good leaving group, do you think hydroxide is a GLG, a good leaving group? Yes or no, why or why not? I think you could probably answer that in words, 10 words or fewer. Well, in terms of assessing leaving group ability, we would want to think about basicity. So a weakly basic thing is typically a good leaving group, except that hydroxide is not a particularly weakly basic thing. So hydroxide is a fairly strong base. So hydroxide, should it be a good leaving group? One word answer, no. So not a good leaving group. Always be sure that when you're writing SN2 reactions, or any reaction for that matter where there is a leaving group involved, that you take a very skeptical view of things if that leaving group is going to be hydroxide. Hydroxide is not a good leaving group. If there's one take-home message from this reaction, that's it. So we really would not expect the left to right SN2 reaction to be particularly successful. This evidently is not a good way to convert an alcohol into an alkyl halide. In the previous problem, we saw how trying to make an alkyl bromide directly from an alcohol by displacement of hydroxide HO- by Br- as the nucleophile was not particularly productive. But let's look at an alternative that does in fact work. Let's start with exactly the same alcohol. So this is ethyl alcohol or ethanol. And then instead of treating this with Br-, let's treat it with HBr, so hydrobromic acid. That's a pretty strong Bronsted acid. And it turns out that under these conditions, you actually get a good reaction in which the alcohol is converted to the corresponding alkyl halide plus another byproduct. So the first part of this reaction is simply balance the reaction by filling in the box. What else is produced in the course of this reaction? The parts that we haven't accounted for yet are the OH group from the alcohol, and then the hydrogen from the HBr. So if you put all that together, you might have guessed that the other product here is water. And this works well. And what I'd like you to do is come up with some rationale for how this works. And a couple hints here. Number one, think of the HBr acting, as you might expect, as a Bronsted acid. And second of all, an SN2 reaction is involved. And in this order, too. So maybe those hints can lead you along a path, propose a rationale for how this might work. Don't forget what we learned in the last problem, that the problem we had in the previous example was hydroxide, HO- is a terrible leaving group. So maybe we've done something to get around that problem here. Well, let's start with this part, HBr as a Bronsted acid. It might be helpful if we just redraw HBr with the bond in between the H and the Br. And if the hint is that HBr is a Bronsted acid, something's going to get protonated. So we have to look around here at the other reaction partner, and we have to find some site within this alcohol that could reasonably act as a Bronsted base and pick up a proton from HBr. So if you didn't get a chance to get this problem started, try that step. We're going to use a pair of electrons from the OH group of our alcohol to pick up a proton from HBr. And so if we think about what that's going to give us, we now have an extra proton on that oxygen. Like that. And then we've released Br-. So there's a bromide that has been generated. Remember to check charge conservation. I had a neutral alcohol and a neutral HBr molecule. I've got an anion here, so there must be a positive charge. And the positive charge goes on this oxygen right here. Okay? Then Br- could come. It could take back its proton. You could go back the other way. So you can imagine a lot of times these Bronsted acid, Bronsted base reactions, you can think of them as being reversible and rapid proton exchange. So you protonate the OH group of the alcohol OH group that's protonated loses its proton, and da-da-da-da-da, sort of back and forth, back and forth, back and forth. look at this structure here and think about where we're trying to go. And remember the hint, an SN2 reaction is involved. Can you finish this reaction pathway? Reaction pathway is sometimes referred to as a mechanism. So can you finish the mechanism for this reaction? Well, it looks like we're really ready here. We can take the bromide now and we can carry out an SN2 reaction. And we now need to break a bond at this carbon that's undergoing substitution, and we can go like that. What is the leaving group in this SN2 step? So here's my SN2 step. What's the leaving group in this particular case? Well, the leaving group is shown over here. There are the products of the SN2 reaction. The leaving group is a molecule of water. So compare the leaving group ability of a molecule of water to the leaving group from the previous example, namely a hydroxide ion. So the next question is, how does this compare as a good leaving group versus hydroxide? Well, remember, leaving group ability tends to parallel the opposite of basicity. In other words, a weaker base is a better leaving group. So hydroxide, its conjugate acid. What is the conjugate acid of hydroxide? You can just type it into the typing part. The conjugate acid of hydroxide is H2O. What is the pKa of H2O? You can't look at your pKa table. You need to know this. To the nearest pKa unit, the pKa of H2O is the pKa about 16. Let's compare that to water. What is the conjugate acid of water? Write it down. The conjugate acid of water is the hydronium ion. What is the pKa of the hydronium ion? You can look it up on your pKa table. Type it into the Zaption. The pKa of hydronium is about -2, more like -1.7 if you want to take it to the first decimal place. But you see, what's the stronger acid, H3O plus or H2O? H3O plus is 18 powers of 10 more acidic than H2O. And so the conjugate base of H3O plus, water, is much less basic than the conjugate base of water, namely hydroxide. All right? So water, our conclusion is, water is much less basic than hydroxide. And maybe you didn't need any kind of sophisticated analysis to say that. But because water is much less basic than hydroxide, water is a much better leaving group than hydroxide was. So the way we got around the problem that we faced in the previous reaction was we avoided having hydroxide be the leaving group by doing a preliminary step where we protonated this OH group. And now we've converted a bad leaving group into a much better leaving group, and the SN2 reaction can proceed. So from a strategic point of view, we've done something that we might call the improve the leaving group strategy. It's sometimes necessary, particularly when your starting materials are alcohols, to improve the nature of the leaving group before you can do an SN2 reaction. Let's continue with this improve the leaving group strategy. again, this is particularly useful and significant when your starting material is an alcohol. So let's imagine that we have an alcohol. So in this particular case, well, let's not use that one. Let's just use maybe this alcohol right here. This is a derivative of cyclohexane. So this would be cyclohexanol. And then let's imagine that we wanted to carry out some nucleophilic substitution at this carbon right here. So say we wanted to replace that OH group with something else. Don't forget there is a hydrogen there that we're not showing in the structure. Maybe we should just to fill things out. So let's say we want to replace that OH group with some nucleophile. We know that we really can't do that directly because hydroxide is such a rotten leaving group. So we could, for instance, run the reaction maybe in the presence of a strong acid. But that's not always compatible with the reaction conditions that you want to use. Some molecules might be acid sensitive. Your molecule might be prone to being protonated by the acid. So here's an alternative to the strategy we saw before, where we protonated the OH and lost it as a molecule of water. How else could we improve the leaving group? So here's what we're going to do. We're going to take our alcohol and carry out a reaction with a reagent of this type. And I hope that you will recognize this group right here, the sulfonyl group. It should make you think of a category of organic molecules called sulfonate esters. And the reason that that's significant in the part of the class that we're in right now is, remember, sulfonate esters were very good electrophiles for SN2 reactions. Except this sulfonyl group has a chlorine attached, so we might call this a sulfonyl. So this would be the generic name, a sulfonyl chloride. And what I would like you to do is I would like you to write down what you think is going to be the product of this reaction. And to give you a hint, I'm just going to tell you that there is a byproduct, and that byproduct is HCl. So combine this plus this, lose this, and get a product that should look familiar in terms of its generic type of structure. Try to keep in this class the black box reactions to a very bare minimum. But rather than worry too much about the details of how this reaction occurs, let's just concentrate on the overall stoichiometry, getting all the pieces accounted for, and then concentrate on what the structure of the product is and what its utility as far as organic synthesis might be. So write the product of this reaction. The HCl that we lose, evidently, it involves this hydrogen and this chlorine right here. So we could imagine if we really just magically excised the elements of HCl and made a bond between this oxygen and this sulfur, that would account for the loss of HCl and the formation of a product that hopefully will look familiar. So another chance to write down that product if you haven't done it already. The product is going to be a sulfonate ester. So here is the new bond between the oxygen and the sulfur. And then all of the other stuff on the sulfur really is just still there. And then let's focus on this carbon here. It still has a hydrogen attached. So one further question for you. Has anything in this reaction, as far as you can tell, has anything happened at the pink carbon yet? In other words, have any of the bonds to that pink carbon been broken during the course of this step? Yes or no? The answer to that is no. So this hydrogen right here was attached before, and it's still attached. This carbon-oxygen bond is still intact. All right? So that's really pretty important. No bonds made or broken yet at the pink carbon. All we've done is put this sulfonyl group on the oxygen of the original alcohol. Okay, so now can we do an SN2 reaction now? So let's pick one of our favorite nucleophiles. At least one of my favorite nucleophiles is the azide anion N3-. In a recent assignment, you wrote a Lewis structure of N3-. It's kind of an interesting Lewis structure. It seems to have charges all over the place. But overall, this anion, sometimes people will write it like that. N3- turns out to be a very good nucleophile. So can you write the product of the reaction between the very good nucleophile, azide anion, and this sulfonate ester? So you have seen examples before of SN2 reactions of sulfonate esters. Can you write the product? Let me redraw the azide anion over here, N3-. Now bonds are going to be made and broken at this carbon, because this is the tetrahedral carbon that's undergoing SN2 substitution. Start your arrow pushing from the nucleophile. Here comes the nucleophile. It adds to the pink carbon. The bond between the pink carbon and the leaving group breaks. And here's a good opportunity to remind ourselves what a good leaving group this sulfonate anion is going to be. So draw the product if you haven't already. The product is going to have the cyclohexane ring. Here's the pink carbon. The pink carbon is attached now to the azide group. There's still a hydrogen attached. And then if we're going to balance the reaction, we have the sulfonate anion that acted as my leaving group. Remember, the sulfonate anion is a particularly good leaving group, one of the reasons being the negative charge is delocalized over these three oxygens. And then if you were keeping track of the counter ion, the sodium ion, you could include that. People often ask, do I need to worry about the counter ion? Generally speaking, no. If you omit it, it's not a big deal. All right? But if you are worried about it, it goes along with where the negative charge is. So this is another improve the leaving group strategy. You start, go back over here. You start with an alcohol. You do a reaction with a sulfonyl chloride. That generates a sulfonate ester as the intermediate. And then you do the SN2, this is the SN2 step, and you get your substitution product. You know two ways now of improving the leaving group when the starting material is an alcohol. You can carry out the reaction in strong acid and then displace water as a leaving group. That is sometimes not a particularly synthetically useful approach because of the need to use a strong acid. This is a more flexible, generally useful alternative where you first convert the alcohol into a sulfonate ester and then you displace the sulfonate anion with your nucleophile. Improve the leaving group, and finally, a reminder, Is hydroxide, HO-, a good leaving group? No, it is not. Let's do a synthesis problem. In a synthesis problem, we're given a starting point. In this particular case, let's imagine that we start with this alcohol. Question, is this a primary alcohol, a secondary alcohol, or a tertiary alcohol? Look at the carbon to which the alcohol or OH group is attached and ask the question, how many carbons is that carbon attached to itself? It's attached to 1 carbon, 2 carbons, so this is a secondary alcohol. Here is the synthetic problem that we will face here. Our job will be to provide some reasonable way to convert this secondary alcohol into this product. This product has an oxygen attached to our all-important salmon-colored carbon here, except now this oxygen is not an alcohol. It's in the form of this functional group, and then there's a hydrogen as shown. Just a little bit of nomenclature review. You see our product contains this carbonyl group. What do you call a carbonyl containing compound that has an alkyl group, or just an R group, a carbon group on one side, and an O carbon group on the other side? What is the name of just this functional group right here? This group is an ester. That's just a little bit of review. So this is what we have to do. In some reasonable chemical way, we have to do a synthesis. We have to prepare, we have to synthesize this compound starting from this compound. So the first level of analysis of a problem like this should always be to compare where we're starting with where we're supposed to get to, and look for whatever we think the major changes in the molecule are going to be. So let's pause the video a little bit and just think of a couple things that you have to accomplish during the course of this synthesis. Well, one thing you might notice is the arrangement of the groups around this, this particular carbon. So did you notice that in the starting material, the hydrogen group is on the wedged line, in other words, is coming out toward you, whereas in the product, that hydrogen group is going back? What do you think is happening at the salmon-colored carbon? One word, and it starts with an I. It looks like an inversion has taken place, a kind of turning inside out of the stereochemistry at that carbon. And then the second part of this analysis is think about a reaction that you know that goes reliably with inversion. And we don't know that many reactions yet, so maybe your options are fairly limited here. This suggests that an SN2 reaction should be involved, because we know that an SN2 reaction occurs with the nucleophile coming from the backside of where the leaving group is going, and so we might imagine that that would lead to inversion. The next thing is, what is the difficulty with trying to do an SN2 reaction starting from an alcohol? So there's a big problem that we faced before in terms of using an alcohol as the electrophile in an SN2 reaction. What's the problem? The problem is that we have a bad leaving group here. So hydroxide is a very bad leaving group. What general strategy should we take? What is going to be our approach when we're faced with a problem of an alcohol that has a very bad leaving group, hydroxide associated with it, but we want to do a nucleophilic substitution reaction? What is the general strategy? The general strategy is to improve the leaving group. So can you think of how we might do this? And again, remember, one way to improve the leaving group is to use a very strong acid like HBr or HI or something like that to protonate the OH group of the alcohol, and then you lose the leaving group as water. That's not generally synthetically useful. So what's the other alternative? What do we do to make the OH group into a good leaving group? Let's take the approach of making the sulfonate ester. So the first part of this reaction is how would you make your starting alcohol into the sulfonate ester? What kind of reagent should you use? Do you remember what that reagent was that we could use to convert an alcohol into a sulfonate ester? Remember the sulfonyl group, maybe we could start there. And then the sulfonyl group has a chlorine on it. And then on the other side, it has some R group. Perhaps the one we're most familiar with at this point is this paramethylbenzene group right here. Doesn't play any direct role in the reactions that we're going to look at, but this is a convenient material. You can buy this in a jar and you can weigh it out and put it into your reaction mixture. So the first step, we might number these steps. Step 1, we would take the alcohol, we take the sulfonyl chloride, and so remember these reactions liberate one equivalent of HCl, an HCl molecule for each pair of molecules that reacts. So write the product, and remember this product is going to be a sulfonate ester. So write the product of this first step. So I'll come over here where I have a little bit more room. In this product, I'm going to make a new bond between this oxygen and the sulfur. Remember from the previous example, nothing is happening at this carbon. All of the action is at this oxygen and at this sulfur, and that's very important for the purposes of this problem because we're really worrying about at this carbon, what's back, what's forward. Notice that the groups that are back and the groups that are forward are not changing here. So in the product, the hydrogen at this carbon is still toward us. The oxygen is still back, except now that oxygen is attached to the sulfonyl group. And here is my sulfonate ester. Again, this is a critical point. Has the stereochemistry at this carbon been altered thus far as we've converted the alcohol into the sulfonate ester? Yes or no? No, the stereochemistry at this carbon has not been altered yet. We still have the SN2 step to go, though, so we have the opportunity now to carry out the inversion. So the final part of this question becomes, what nucleophile would I choose to react with this sulfonate ester in order to give me this product? So supply the nucleophile for this final step in the synthesis. We need something that is going to incorporate all of these atoms and that is going to be a pretty good nucleophile. So I'll just kind of orient this in the same way that it's shown in the product. What if I used this anion as the nucleophile? I might need some counterion to go along with this. So maybe sodium. That ought to work, right? Because now this anion, which is a pretty good nucleophile, is going to come in. It's going to react with this carbon. It's going to displace this leaving group, and it's going to give the final product. What is the name of this anion? Could you type that in? This is the conjugate base of acetic acid. This is the acetate anion. It's a carboxylate anion. That's a little bit redundant. Carboxylate must be an anion, but anyway, there you have it. And then the last question I want to ask you here is, from this synthesis, is this oxygen, that one of the alcohol, is that the same oxygen in the product? Yes or no? No, it isn't. It's a different oxygen. This oxygen came from acetate, and this oxygen was lost as the sulfonate anion in the SN2 reaction. The other important thing, since you really haven't done any organic chemical synthesis problems before, I don't think, this is a two-step process. So imagine you're going to go in, you're going to do this process in the lab. Lab period number 1, you make the sulfonate ester. You purify the sulfonate ester, maybe by recrystallization or whatever. You have the sulfonate ester, you put it in a vial, you put it in the drawer of your bench, and then you go home and you come back to the next lab period and you do the SN2 reaction. So in chemical synthesis, we'll often number steps to show that these are discrete operations. First you do this step, then you do the next step. You could certainly have a longer sequence where then you do step 3 and step 4 and step 5, however many steps it takes. This is a general approach for improving the leaving group by making the sulfonate ester from an alcohol. And the thing that really gave us a hint that an SN2 reaction was going to be involved was the observation that we needed to have inversion at this carbon. So be on the lookout for reactions that are telling you, hey, we need inversion, and an SN2 reaction might be involved.